Imagine handing a brilliant assistant a massive library of documents, but as soon as they read the second book, they completely forget the first one. This phenomenon, known as context rot, limits how effectively modern large language models can process massive datasets. Today, we explore how researchers at MIT CSAIL are solving this with recursive language models. The core problem is that as the input length for a model grows, its ability to reason about that data drops, often well before it hits its hard token limit. The researchers describe this as context rot. Traditional fixes, like summarizing the text or using retrieval algorithms, are lossy. They discard details that might be crucial for complex reasoning. This rot is particularly damaging when tasks become information-dense. While standard approaches can find a single needle in a haystack, they fail at quadratic tasks, like comparing pairs of arguments across thousands of documents. The authors argue that merely scaling the context window isn't enough. We need a way to maintain dense access to specific details without overwhelming the model. The big idea here is a paradigm shift. Instead of stuffing the prompt directly into the model, the researchers treat the long context as an external environment. Drawing inspiration from out-of-core algorithms in systems programming, the large language model interacts with the data symbolically. It doesn't memorize the file, it learns to navigate it. To implement this, they place the model inside a Python REPL. The massive text prompt is loaded simply as a string variable in persistent memory. The model receives metadata, like the string length, and can write standard Python code to slice, search, or decompose that string. This keeps the model's active memory clear for reasoning, rather than storage. Where this gets truly powerful is recursion. The root model, acting as an orchestrator, can use a special function called RLM. This allows it to programmatically trigger subinstances of itself, or cheaper, smaller models, to process specific chunks of data. These submodels return summaries or answers back to the REPL, allowing the root to synthesize the final result. Does this recursive approach actually work in practice? Let's look at the evidence provided by the researchers. This chart illustrates the dramatic difference in stability. As the context length scales up, the standard GPT-5 model, shown in the darker color, sees its performance degrade rapidly. In contrast, the recursive language model maintains high accuracy even when inputs are 100 times larger than the base model's limit, handling over 10 million tokens efficiently. The gap is most visible on complex tasks like Oolongee pairs, which requires reasoning about relationships between multiple parts of a text. On this benchmark, traditional models fail almost completely with an F1 score near 0. The recursive approach, however, achieves a score of around 58, proving it can handle tasks that demand deep, quadratic reasoning. Of course, this method isn't without trade-offs. The authors note that the recursive calls are currently synchronous, which can make the process slow. Additionally, there is high variance in how many steps a model effectively takes to solve a problem, and for very short prompts, the overhead of writing code can actually make performance worse than a standard baseline. Despite these limitations, the implications are significant. Recursive language models are often cheaper than full context ingestion because they selectively view only what is necessary. This moves us beyond simple retrieval augmented generation, offering a path toward processing infinite context environments, where models act as agents over data, rather than just readers. To learn more, head to emergentmind.com.